Hey everybody, in this video I'm going to walk you through a method or a process for comparing the first ionization energies of a set of atoms, in this case sulfur and selenium. To do this, we're going to use the table that you're looking at here. You don't necessarily have to recreate this table yourself, but this table does walk you through some steps to follow to make any first ionization energy comparison that you come across. The whole thing starts off with writing the electron configurations for each atom. You can do this, in the unabbreviated form, starting with 1s2, which I'll do for sulfur. You can also do this in the abbreviated noble gas notation, which I'll do for selenium. And it's important to do that first because if you can't see where each atom's electrons are, then you probably can't answer the question or compare their first ionization energies. Once we've got that, we're going to start analyzing what we can see in those configurations, starting with, very simply, what is the outermost energy level that the electrons fill to. For sulfur, they go into the 3s's and the 3p's, otherwise known as the third energy level. In selenium, they go into the 4s's and the 4p's, otherwise known as the fourth energy level. That difference is going to be important later on. The next thing we're going to look for is how many shielding electrons each of these atoms has. Sometimes these might be called the inner electrons, pretty much anything that's not one of the valence electrons. For sulfur, that's going to be all the electrons in the first and second energy levels. So I've underlined those in green on the configuration, and if you counted them, that adds up to 10 shielding or 10 inner electrons. If you do the same thing for selenium, its inner electrons are all of those represented by the symbol Ar, which is 18 electrons, plus the electrons in the 3d10. That 3d10 is still technically part of the third energy level, and therefore still technically part of the inner electrons, giving us a total of 28 electrons for selenium. Next thing we need to compare are the nuclear charges of each atom. That is simply how many protons each atom has. Sulfur has 16 protons with a nuclear charge, therefore, of plus 16. Selenium has 34 protons with a nuclear charge, therefore, of plus 34. Notice selenium's nuclear charge is greater. All of this leads to one of our other very important comparisons called effective nuclear charge. Effective nuclear charge says if sulfur has a nucleus with a plus 16 charge, that is canceled out by those 10 shielding electrons that we counted earlier to give what is effectively a nuclear charge that is plus 6. If we do the same thing for selenium, it has a nuclear charge of plus 34, but that 34 is canceled out by 28 shielding electrons that we counted earlier. This gives us a effective nuclear charge for selenium of plus 6 also. So we're going to wrap this up by looking back over all this information and pointing out the two comparisons that really matter, or the two comparisons that will actually give you a result, give you an answer or a prediction here. Those are effective nuclear charge and outermost energy level. What you might notice is that sulfur and selenium both have the exact same effective nuclear charge. That means between these two atoms there is no difference in that particular factor. There is a difference, however, in outermost energy level. Selenium's electrons are in the fourth. And that matters because the final thing we have to do to actually come up with a prediction here is analyze how attracted the outer electrons are in the nucleus. And the effective nuclear charge being the same means that that is not going to impact that attraction being strong or weak. However, as we just pointed out, selenium's electrons are in the fourth energy level, which means those outer electrons for selenium are farther away from the nucleus. And if they're farther away from the nucleus, they're going to experience a weaker attraction to it. So I'm going to label this with those two important points. They're farther away and more weakly attracted. You could do all the same things for sulfur, except sulfur's outermost electrons are in the third energy level. So they are closer to the nucleus, and therefore they're going to be more strongly attracted to that nucleus. This matters because this explains the difference we see in first ionization energy. The whole point of this entire comparison If electrons are more strongly attracted to the nucleus, it's going to take more energy to remove them, which means sulfur, we would predict, is going to have the higher first ionization energy. This also means that selenium, we would predict, is going to have the lower first ionization energy. And as I said at the beginning, if you force yourself to walk through all of these steps, you can compare any set of atoms in terms of this ionization energy property.